This is carbonic acid. It has this specific structure here, a carbonyl group and two hydroxyl groups attached to it. Now for this video we're going to really be drawing upon the knowledge from the previous videos. So if we're going over things pretty fast and if it doesn't entirely make sense to you, please go back and review the earlier videos in the series now, because we're going to be building more and more on that knowledge base. Now this carbonyl oxygen, as we explained in the previous videos, this is sp2 hybridized, and it has two lone pairs of sp2 electrons. The hydroxyl oxygens, they also have a pair of sp2, lone pair of sp2 electrons, but more important, they have a lone pair of pi electrons, which means that we should be able to set up a resonance system here, and that's what these different canonical forms demonstrate. And again, what we're going to do here is what we've been doing in the previous videos. Here we have a pi bond between carbon and oxygen. This has a pi electron. The oxygen donates a pi electron. They're sharing them between them with a pi orbitals overlap, as we showed in the previous videos. Then we imagine that oxygen keeping both of the pi electrons for itself to have a lone pi electron here with a negative charge. What happens then is we can imagine one of these lone electron pi pairs moving in to form the double bond here with carbon. This pi bond no longer exists, just has the single bond to oxygen. So let's do it like this. Let's write the hydrogen here, and then these move in to form the double bond with carbon. So oxygen is donating both the electron pair to form this bond, so oxygen is going to have a positive charge on it. The carbon doesn't have any charge because it lost its electron to this oxygen, so this remains neutral. So here is one canonical form, or instead of this lone pair of pi electrons coming in to form the bond, it could happen instead with this oxygen. And we would have this canonical form. Notice that these are symmetrical. Here we have this bond. If we just rotated the carbon 180 degrees, this would be here, and this would be over here. So these are symmetrical structures. As we explained in the previous videos, when you're drawing different canonical structures, when you have symmetry, that does have a particularly strong stabilizing effect whenever you have symmetry existing between the different canonical structures. Now, here we also have separation of charges. Not ideal, but permissible. And of course, we have the separation of charges here. But for carbonic acid, notice then that we have this rather extensive, fairly respectable resonance system, leading us to believe that perhaps this is not a very active molecule. If it's so stabilized, then it would just be inert. But let's see what would happen if it did lose one of the protons here. So we're imagining this. We have the two hydroxyl groups connected to the carbonyl carbon, and we lose a proton, so we have it like this. Okay, now as we explained, these hydroxyl oxygens, they have a lone pair of pi electrons. So if the carbonic acid loses a proton, indeed it's acidic, here's the anion. Does this have resonance stabilization? It does. Let's compare the resonance stabilization of the resulting anion with the protonated form of the molecule. So let's go down to here. We're going to take now this molecule. Hydroxyl group. Oxygen with a negative charge. It lost a proton. These are the lone pair pi electrons. And again, just as we've been doing all along, we imagine oxygen keeps both of these. Now these come in, so we have this structure. Oxygen now has a lone pair of pi electrons because it stole one from the carbon. It was donated to this bond. This one was donating an electron to the pi bond. This keeps both of them, so it has a negative charge. But now this oxygen donates its pi electron pair to the carbon to reform the double bond. So this should have a positive charge, but a negative charge to begin with. So of course it has no charge. Now notice that here, these are symmetrical. If we imagine taking this and then about this bond just rotating it 180 degrees, this would be up here and then this would be down here. So these are symmetrical. Notice also now that unlike the protonated form of carbonic acid, there's no separation of charges. What we have here is the charge is down here, now it's here. We have charge dispersion. That's always preferred over charge separation, plus we have the symmetry. So we have symmetry with charge dispersion. That's a better resonance stabilization system compared to when you have charge separation. What's more, the electronegative oxygen here has a positive charge on it. Again, it's permissible, but not very desirable. Here, whatever oxygens that we have a negative charge on them. Now we can form one other Lewis structure, another canonical form. Suppose that instead of this oxygen donating its electron pair to form the double bond, suppose this hydroxyl oxygen does. So then we would have this structure. Like this. Now here, this was neutral. It donated the electron pair, so now it has a positive charge. And these are, well, yes, and then these are the same. So now notice that in this canonical structure, we have separation of charges, and the electronegative oxygen has a positive charge on it. Again, it's permissible, but not desirable. But the point then is that the anion that results when you lose the proton gives these 1, 2, 3 canonical forms. These are very good canonical forms, and you have the symmetry. So even though the protonated form of carbonic acid has a fairly decent resonance system so that it's somewhat stabilized, it still is motivated to lose one of these protons to form this anion because the resonance is an even better system. Now we could probably ask this question: what would happen if the carbonic acid lost not one proton but lost two protons? So that what we would have is this. See if we have enough room to write it. We would have and now this oxygen would have a negative charge because it lost its proton. Now what kind of resonance structures can we draw? Again, both pair of electrons go to this oxygen. The pi bond is lost. We have a single bond. This carbon has a negative charge. Now, this carbon can donate its lone electron pair to form the double bond with carbon. So what we would have is that double bond. This had a negative charge. It put up both electrons, so now it's neutral, and we have this one. With the negative charge it already had from the proton that it lost. These are symmetrical. Now instead of this, these structures here have symmetry. Now instead of this oxygen donating its electron pair, its pi electron pair, this oxygen could do it, and we would have another canonical structure. This is getting crowded now. Like this. And again, this is symmetrical. And no separation of charges here. It's all charge dispersion. So if this carbonic acid, when it loses a single proton to form this anion, we have a very good resonance system, so it's motivated to do that. If it loses both protons, we have a very powerful resonance system. But yet, for this to lose both protons, it very rarely happens, even though we have superior resonance. And the reason is, when you lose both protons, this anion has a double negative charge. So the proton that it loses, it has a positive charge. This is a relatively small molecule. These are all second row elements, carbon and oxygen. So you have this very small molecule with a double negative charge. When this loses that proton, you have this powerful negatively charged molecules pulling the proton back. So for this to lose its proton, even though we have this very powerful resonance system, it's very difficult for this oxygen to lose the proton to set up this powerful resonance because of the double charges that exist on the resulting anion. It's going to pull that proton right back onto that oxygen. So here's an example of a molecule that you'd think could be very acidic because of this powerful resonance system, but because of other factors that are involved, this anion right here is not going to lose that proton. So for carbonic acid, it's set up, so to speak, that it can lose one of these protons to set up a fairly decent resonance system, but it cannot lose both protons to set up this very superior resonance system because of the double charges that result in the anion. Okay, that's it then for this example. Again, the playlist for all the videos is at the website digital-university.org.